Here we have our beginning, our amplitude modulation reception. And if I need to go back or stop or whatever, please just let me know. All right, so here we have our breakdown or block diagram of what's going on the reception side. As you can see, we have our antenna right here, which is going to be receiving the signal. And what kind of signal am I receiving at this point right here?
In the antenna, you receive.
What's coming in? What is literally coming in at that point?
The carrier.
Okay. And
the intelligence.
The what?
Intelligence.
Okay, so when we put those together, we have a
signal.
We have a modulated signal, right?
Oh, okay. Yeah. Oh, yeah. Right. Yep. And then you got it. And you're trying to say both sides of the intelligence are coming in.
What? No. What I'm trying to say is that remember all the stuff we've learned so far about modulation, how we took the intelligence and the carrier and combined them in which is what we did. And that's what we call modulation. We put them together and now we're modulating that signal out into the atmosphere.
Gotcha. And it's one signal.
It's like one signal. Very good. That's what I'm looking for. One signal combined. So all that is coming into our antenna. Then we have our RF amplification. Okay, remember, like I said before, we don't know how far it's been since it was amplified. You know, not like a cell phone tower, how you have repeaters. When it starts getting further and further out in the country, we need to amplify that signal to keep sending it out. So in this case, we need to amplify it so we can actually start to remove all the stuff that we need to remove from it to get the intelligence. Then we have a detector. Or don't worry, we're going to go through each one of these individually and break them all down. Then we have our detector, which is the detector part is, we'll see that here in a minute. Basically, it's just more or less a diode, and it allows half of that envelope to pass through. Because if you remember, on the full envelope, we have what?
You have two intelligences.
There you go. Exactly. And they're both identical, correct?
Yep.
All right. Then we have, once we remove that, once we go through the detector, then we're going to go to our audio amplification. And basically, this is oversimplification. But anyway, it comes out through our speaker and we hear whatever's going on, if it's a radio station, an announcer, or whatever. So this type of receiver is known as the TFR, the tuned radio frequency, because it contains an RF amplifier, detector, and audio amplifier. And yes, all this information on the PowerPoint and labs and everything else in the book is all going to be testable material. Hey, like I say, this is the basic breakdown of a reception side of the AM modulated signal. All right, so now we have, oh, sorry, went too far, didn't I? Oh, no, it didn't. So now we have our terms. These are our breakdown of our terms. Our sensitivity basically is just the ability to drive the output transducer or speaker. And when we say transducer, what example did I give you guys about the use of a transducer? Where would we might actually see a transducer? All right, remember transducers are they're low frequencies. Sometimes you can't hear them, but you can feel them, correct?
Right, so the base of a speaker, is that what you're saying?
Yeah, something like the base of a speaker, or they're actually, transducers are like a cylinder object that has a cone on top and bottom. They're fastened together between in the center, and then you mount those. You physically mount those underneath chairs or whatever. And like before, you might see them like at Disney or something where they have the dinosaurs walking around on the back of the seats. You know, you feel those vibrations. You don't necessarily hear them, but you feel them. So that's our sensitivity, okay? Our selectivity is the extent to which a receiver is capable of differentiating between the desired signal and other frequencies, or the unwanted radio signals and noise. That's our selectivity. Our diode detector, which we talked about earlier already, is one of the simplest and most effective types of detectors, and one with nearly an ideal nonlinear resistant characteristic. Diode detector, also known as the envelope detector, is used for removing the carrier frequency from the intelligence signal. Okay, the advantages of diode detectors: one, they can handle relatively high power signals. Right? There's no practical limit to the amplitude of the input signal. Distortion levels are acceptable for most AM applications. Distortion decreases as the amplitude increases. They are highly efficient. When properly designed, 90% efficiency is obtainable. And they develop a readily usable DC voltage for automatic gain control circuits. And we'll see all this stuff in a little bit. Okay, so we have the disadvantage side. So with the disadvantage, we have power absorbed from the tuned circuitry by the diode circuit. This reduces the Q and selectivity, which is not good for us, of the tuned input circuit. No amplification occurs in a diode detector circuit because all we're doing is removing stuff. Let's start looking at the circuitry. Here we have our diode detector circuit. So let's look at this for a moment. Who can tell me what part is this referred to as?
No, it's not the latch, but it has something to do with
What do we call that? We've already talked about it.
It had something to do with the oscillators that we looked at. I know that.
Okay, and so what do we call that, Thomas?
It's not a latch circuit. It's
No. Remember, we're receiving the AM signal coming in. So we need to be able to do something in order to receive it.
Amplified.
No.
Demodulated.
Okay, let me ask you this. Let me remove this for a second. What do you think?
Tank circuit. It's a tank circuit.
Okay, Thomas. All right. It's a tank circuit.
I had to look in my test.
Okay, so it's a tank circuit. So in order for us, this tank circuit serves a purpose. And this is what we call that variable capacitor, or a what? What was the other name for this?
The tuner dial, right?
Right, tuner, but it's called a varactor.
Oh, yeah, you're right. Because I tried to remember that with the very nice, Borat guy.
Right. So this is our tank circuit, and this is what we use. This is a variable capacitor, and we have to tune this in order to select. Remember selectivity. We're tuning it in to select the station that we want it to pass through. And then we have our diode detector here, and then we have our other components here for allowing it to pass through. And then we have our coupling capacitor here. And don't worry, we're getting ready to go through each one of these stages. So just know that this is our basic diode detector circuit. And we're going to be looking at the output signal of this. All right, so here we have our first waveform coming out. Okay, this is our first waveform coming out. This is the input signal of the diode detector or the modulated carrier. So at this point, this is what's coming in at this point right here. So all this is we got all this circuitry to go through in order for us to start to extract the intelligence from this circuit. So the first thing we do is the waveform is before the diode, as we said. The second part is the modulated waveforms show both the upper and lower envelopes. Remember, this top part here is exactly the same information as the bottom part. And we only need one side of that envelope. There's no need for us to actually bring in two carriers with the same information or two bits of information from the same carrier. They're both exactly the same. And when you design your circuits and you start doing your stuff, just remember, it's really up to you which side you want to remove, the upper or lower. So, but you'll see more about that later. Then the amplitude of the waveform is that of the intelligence signal, as you can see. And the components L and C1 make up our tuned circuit, which is our tank circuit. And it is tuned to the resonant frequency of the AM signal coming in. So these are all the more defined bits of information that we need to know about our input coming into our tank circuit. Next stage. So here we have, what point do you think we're at now with the bottom half of this signal being removed?
So the bottom half is cut off, so it's basically a half wave rectifier.
Okay, so it's a half-wave rectifier. Now, what you need to understand is, so let me remove this part of the drawing here. How do we know by looking at our circuit that this is the correct signal to pass through?
We can check the capacitor next to the inductor.
Nope. How do I know that that is the correct part of that signal to pass through this circuit? What component do I need to look at? And when looking at it, how do I know it's the correct one?
The diode, correct?
All right, the diode, that's step one. Step two, how do I know that that's the correct output? By looking at my diode. You guys have to have a flashback here of what this half-wave rectifier actually does.
Is it based on the bias of the diode? Forward or reverse? If forward or reverse bias, it depends on the.
Okay, so let me ask you guys: is the diode in forward or reverse bias with that output?
Is it forward because it starts positive?
Okay, all right, Matt, good job. So here we have our anode, correct? Which is the positive side of this diode. So when our positive peak of this signal comes in, guess what? It forward biases this diode and allows us to pass that through. You see how we have our positive peaks? And every time the negative side hits this, it reverse biases it and cuts it off. And hence, we lost our bottom half of the signal. Does that make sense?
Yes.
Oh, now let's see what's happening here. So now we have the average input voltage is 0. Okay, the average input voltage is 0, and the average output across R varies above 0. Now, this is a low-pass filter developed with the components of C2 and R. So here we have a low-pass filter, which are used to remove the carrier frequency itself. So now we've established a reference line, and the whole signal is above the 0 on this output. This is what it looks like with C2 disconnected. Now we have C2, this is the peak output with C2 in the circuit or connected back up. So with C2 in the circuit, the output voltage will vary as it follows the peak variation of the modulated carrier signal. Because remember, audio is modulating up and down. Then since the peak voltage varies with the modulated carrier signal, it is sometimes referred to as the envelope detector. The envelope detector. Remember, all this information is before going into C3. So all this information right now, or that signal, is basically before we go into our C3 capacitor. Now let's look at the output of C3. Now we have our signal coming out of C3, which is the last part, which is right here. And the DC component produced by the detector circuit is removed by the capacitor. Why? Because a capacitor does what? What's the function of a capacitor here with reference to our DC component? Guys, got to remember how a capacitor works.
Like a battery, right?
Well, what's the relationship with the capacitor and AC voltage and DC voltage?
Once it I believe once it charges up, it acts like an open switch.
No. Basic capacitor function from your first day of class 5 years ago.
You mean like how they're built?
Do what now, Matt?
You mean like how they're designed, plates?
Well, how do they work in relation to DC and AC?
When they charge up and discharge, the DC does, it works like a battery and a switch.
Okay, yeah, you got that's correct, but how does this actually function as a coupling capacitor with AC and DC? I mean, you're right, it does charge up and all that kind of good stuff, but how does it actually physically function as a coupling capacitor?
Well, the charge moves through the two plates or whatever. Is that what you're asking?
No.
I'm confused then.
Okay. So this is a flashback. A capacitor. With AC, a capacitor allows AC to pass through its coupling capacitor. When it comes to DC, it blocks DC and passes AC. You remember that? It blocks DC and passes AC. So that's why we can say that this signal that's coming out right now, right here, is no longer moved above the reference line because the DC component produced by the detector circuit is removed by capacitor C3. The use of DC component is often used for an automatic volume gain in this circumstance. So right here, if we remember, DC is blocked and only allowing the signal itself, the AC signal, to pass through. Does that make sense? Do you remember that?
It's vaguely familiar, but what I'm wondering is, what does that have to like? I don't know how to ask the question. Like, isn't circuit either AC or DC, not both?
Well, no, we can have DC points. We can have like in this circuit here, we can have DC values, right? But we don't want to pass through the DC. We just want the AC signal, or basically the intelligence signal, to come through. We don't want to establish a new reference.
So you're not having power coming through the thing. You're just having the voice coming through. Is that what you're saying? Otherwise, you basically would have like a live mic, literally.
Right. So when we had this at this point right here, before this, remember we had this signal all above the 0 reference point. Remember looking at your oscilloscope, how it's DC coupled and sometimes it's AC coupled?
Right. I see what you're saying now. Right, the sine wave, it turned the wave from a DC wave to a sine wave.
Right. Well, basically it changed. I know you guys have seen this before. On your oscilloscope, you have DC coupling and AC coupling. DC coupling means that you've established you're using a DC reference point like this right here, saying my value is going to be above the DC reference point. If I change that to an AC coupling, okay, then it's going to ignore the DC reference point and it's going to bring it right here at the 0 reference line and give me that positive pulse and that negative pulse right in the center of this. And I know you guys have seen that before on the oscilloscope. So anyway, what this is doing is this C3 is removing that DC component that's inside this circuit, this detector circuit. That's all it's doing. And giving us that clean signal coming out. Well, of course, that's not super clean, but anyway, you know what I mean. Any questions on that? Okay. So continue with our terms. So we have a product detector. Now, a lot of these terms and stuff, we won't be actually applying into our circuits, but they are synonymous to some others, so you need to be familiar with them. So the oscillator, mixer, and low-pass filter stage is used to obtain the intelligence from an AM signal. This is the product detector. The noise floor is the baseline of a spectrum analyzer, which you guys have been using, representing input noise of the system under test. So you can actually determine if there's noise in the system itself on the receiving side of the modulation of the AM signal. And then we have our synchronous detector, which is another name for the heterodyne detector or the product detector. Like I say, a lot of these are synonymous, but you will need to know them. The synchronous detector is used when greater performance is demanded. And a lot of this demand of these different types of detector is really based, a lot of it's based on cost. So the advantage of the synchronous detector are one, slow distortion, usually well under 1% in this case, greater ability to follow fast modulation waveforms as in pulse modulation or high fidelity applications, and then also the ability to provide gain instead of attenuation as a diode in a diode detector. So these are just a few of the advantages. And then in just a second, we're going to look at the breakdown of a super heterodyne receiver block diagram and go through the stages. Okay, so don't worry, we're going to go through this whole process here and explain everything. So here we begin. This is our super heterodyne receiver block diagram. We have our antenna. Same principle as the detector circuit. We have our amplitude or modulation signal coming in. And we have our RF stage, which in this case, we have tied to a local oscillator. And we're going to talk more about all this, so hang tight. After these go through, we got a mixer. These values we come through here, mixer, and this mixer will be producing a multitude of different frequencies based on whatever is coming into our antenna. Then we have our IF amplifier, which is our intermediate amplifier to amplify the signal after the signal has been mixed. Then again, we have our detector circuit, which feeds back into our IF amplifier and back into our automatic gain control circuit, which is underneath here, all this. And then after that, it goes to our audio and power amplifiers, and then eventually to our output speaker so that we can hear what is actually being sent or received on our AM signal. So get this down, get this block diagram down, and then we will talk about the stages. So the first thing, let's start breaking this down. Our RF stage. This is used to amplify the incoming modulated signal. The mixer that we just talked about accepts two inputs. Okay, the output of the RF stage and a steady sine wave from the local oscillator that was down below. And then the mixer is a nonlinear device and is used to mix the AM signal with a sine wave to generate a new set of sum and difference frequencies. And we talked about that already. Its output is an AM signal with a constant carrier frequency, regardless of the transmitter frequency. So because of the local oscillator, we're able to continue to have those constant carrier frequencies, all right? The sum and the difference. We're going to look at values here in just a little bit. All right. Next, we have our intermediate, the IF that we talked about, which is the intermediate frequency amplifier. This provides the bulk of the radio frequency signal amplification at a fixed frequency. This allows for a constant bandwidth over the entire band of the receiver and is the key to a superior selectivity of the super heterodyne receiver. Our detector, just like the same principle that we went through earlier, is used to extract the intelligence from the radio signal. All right, so now we start to look at the conversion process. And we're going to break this down a little bit. But as you can see, we have our local oscillator, which is set at 1455 kHz. This tuned circuit is at 1000 kHz. And then we have our AM signal with its variances of the 1K and then our difference and our sum. And then on the output of our mixer, we have a value or a mixed value of all three of these components right here combined. So we have sums, we have differences, and these are the values of those sums and differences based on the local oscillator, the 1000 kHz tune circuit, and our AM signal coming in. Then we have here our IF, which is our intermediate frequency amplifier. And on this signal right here, it is tuned to the 455 kHz. And as a result of that, we have that 455 kHz on the output. We have our difference and we have our sum for the output. And we're going to explain each of these here in just a second. But this is the overall view of what's happening with our input signal right here, based on the fact that we have this tuned circuit inside here and we have a local oscillator that is also tied to our mixer. All right, so let's look at this a little closer. So in this case right here, we have our AM signal into the mixer, which is right here, this point coming into the mixer. Hey, this is a 1 kHz carrier that has been modulated by a 1 kHz sine wave, a 1 kHz sine wave, thus producing the side frequencies of 999 and 1001, which is right here. That's the first part. Okay, so this is the first part of our coming out of our mixer with our input signal from the AM. All right, step 2. So now the mixer, being a nonlinear device, will generate the following components. Remember, this mixer has information coming from here and it has information coming from here. So the frequencies at all the original inputs of 999, 1000, and 101 kHz and the 1455 kHz from our local oscillator. Then we have the sum and difference components of all the original inputs, which is our 1455 oscillator right here. Then we have our 999, our 1000, our 1001. Again, this means that the outputs at 2454, at 2454, 2455, and 2456, which generates these values right here using our mixer and the local oscillator. Then we also have our other end, which is our 454, 455, and 456 here when we remove the 1 kHz, which is our upper and lower. And then we have our harmonics. Now, harmonics are a big part of this, and you guys have seen harmonics already in your past labs. So harmonics of all the frequency components listed in A and B, all right, and a DC component that we talked about before in the detector circuit. So all these signals right here, all these values are being generated based on this AM signal coming in and our local oscillator. Remember, these are sums and differences of each of these. Now we're going to be talking about the IF. We have our IF amplifier is a tuned circuit that accepts components only near the 455, okay? And in this case, it's just 454, 455, 456. So these values right here. The only thing that this really accepts for our intermediate frequency amplifier is the value of these three. The mixer will maintain the same amplitude proportion that existed from the original AM signal at the input, which were these three right here. So our amplitude has not decreased. We still have that same amplitude coming through. And then the signal that now passes through the IF is a replica of the original AM signal. The only difference is now we have a different carrier frequency, which is going to be based on this 455 kHz. So we still have, this is important, we still have our same information. It's just that it has been transferred or put onto a different carrier value, which in this case is 455 kHz. So we have not lost our intelligence. So this is reiterating what we just said. Here we have the frequency conversion that has now occurred, that has changed the carrier, like we just said, from 1 kHz to 455 kHz, a frequency intermediate to the original frequency, which leads us to the terminology, intermediate frequency amplifier or IF amplifier. Also, since the mixer and detector both have nonlinear characteristics, the mixer is often referred to as the first detector. Okay, this is general information for this superheterodyne. All right, finally. So electronic tuning, one of the best methods for tuning relies on the capacitance offered by a reverse biased diode. Right, keep that in mind. Since the capacitance varies with the amount of reverse bias, a potentiometer can be used to provide the variable capacitance required for tuning or selectivity. And diodes that have been specifically fabricated to enhance this variable capacitance versus reverse bias characteristics are referred to as a varactor diodes. Now we're looking at varactor diodes. Also, it's also can be called varicat diodes and VVC diodes. So this is additional general information regarding the superheterodyne receiver.